Hello and welcome to Engineering Economy. This is Dr. Oleg Kammerziner. We will talk today about the rate of return analysis. Specifically, we will discuss the definition of internal rate of return. We will talk about how to perform calculations of rate of return. Specifically, we will talk about incremental rate of return analysis and discuss decision criteria that are used when using rate of returns analysis, and also how to solve rate of returns using spreadsheets. So we have the following learning objectives for today, and that is to understand and calculate internal rate of return. We will also apply rate of return in decision-making process, and we will understand common assumptions in solving economic analysis problems. Let's take a look at this interesting vignette. Barcodes give a number, RFID codes tell a story. Radio frequency identification, also known as RFID, versus barcode technology. No line of sight requirement when using RFID. RFID tag can stand a harshing requirement. Also, RFID has a long read range. It includes a portable database, multiple tag read and write, tracking people, items, equipment in real time. And there are numerous applications for RFIDs, including logistics and supply chain, in manufacturing, wholesalers, retailers, and in military. So there's a growth rate of RFID, which is increasing at 50% annually, imply anything about the rate of return on the individual projects that support the growth. Another question for you to think about is, what are the cost and benefit factors that should be considered when comparing RFID with barcode? What could be some new applications of RFIDs? Does RFID invade privacy? What ethical and social concerns are raised by RFID chips? So some of the interesting points that we will raise today is the growth and what type of growth or what type of rate of return different projects might have, and how to calculate the rate of return. So the rate of return analysis is actually the most frequently used exact analysis technique in the industry. Why? Well, it provides major advantages, including the rate of return is a single figure of merit that is readily understood. And also, calculation of rate of return is independent from the minimum attractive rate of return, or MARR. And if you remember, the minimum attractive rate of return is actually the rate of return that firm or a company sets for itself in terms of being able to, have the return on the investment. Because if they invest their money into a project, they want to have a certain growth because they might have some financial obligations, or maybe if it's a publicly traded company, they want to benefit the stockholders. So the minimum attractive rate of return is the return or growth of the money that is invested that is the smallest acceptable to the company. All right. So the interest rate at which the present worth and equivalent uniform annual worth are equal to 0 is giving it gives us internal rate of return. So of course that interest rate is an important interest rate, and it represents the rate of return for the specific project. So again, we can have two different perspectives. We can have a perspective of borrower or a lender. So if we assume the borrower perspective, then the interest rate that's paid on an unpaid balance of a loan such that the payment schedule makes the unpaid loan balance equal to 0 when the final payment is made. So this interest rate is our internal rate of return. Of course, we could have a different perspective. We could have a perspective of investing or lender's perspective. From the lender's point of view, internal rate of return is the interest rate that's earned on uncovered investment, such that the payment schedule makes the uncovered investment equal to 0 at the end of investment life. So again, it's just two sides of the same coin. Whether we're looking at it from the borrower perspective or from investor perspective, the point is that when we consider a project and look at all of the cash flows in the project and then find either its equivalent present worth or its equivalent annual worth and set them to 0, then getting the interest rate that turns it to 0 will give us the internal rate of return. So once again, right, it's just two different perspectives, but it still boils down to the fact that assuming any of these specific perspectives, a single one, at each time, if we look at the equivalent present worth or the equivalent annual worth of the project cash flows, then this interest rate would turn this to 0. Here's an example. 5,000 is invested in 5 years at a rate of return of 8%. So now, right, this can be represented through this table as we have this cash flow where 5,000 is invested, and then we are recovering it each time, recovering some portion of the investment. So during the first year, the unrecovered investment is the beginning of the year. So this is from, of course, perspective of the investor, the second perspective, or lender's perspective. Then we have the 4,000 being the return on recovered investment. The way we obtain it is we simply multiply this 5,000 by 8%, and that gives us the interest rate. So then the investment repayment for at the end of the year, that's what we have in terms of repayment, right? And that's the difference between the cash flow amount, right? Because we're representing it as annual worth, right? We represent this investment of 5,000 as annual returns equal annual returns. So we represent it through as a uniform series. So this is equal at 8% to 5,000, right? Is equivalent at 8% to this annual amount of $1,252.28. So then, if we subtract the interest payment from this annual amount, then we will get $852.28, which is investment repayment at the end of the year. So that's the amount of the investment that was paid back to us by the end of the year. And so here we also have an unrecovered investment at the end of the year, and that obtained by simply subtracting this 852 or adding this 852 to the negative 5,000, right? Or if we take the 5,000 and subtract 852, we'll get exactly $4,147.72. Again, that's an unrecovered. This is recovered portion of initial 5,000. This is unrecovered that is remaining. And so again, we are continuing like this till the whole investment is repaid at the end of 5 years. So that gives us, in terms of return of unrecovered investment, that is all the interest rate that we got, and then we have the full recovery of our $5,000 investments. So that again, right, that is the rate of return. We have a rate of return of 8%. So in this case, right, this turns to 0 when we have this cash flows as follows. that gives us a present worth to 0, or the annual worth of 0. When we have all of these cash flows at, of course, 8%. At a different interest rate, it wouldn't turn to 0. But you can see that at the end of 5th year, we get 0. So how do we calculate the rate of return? Well, first we convert various consequences of investment into cash flow. And then we use one of the following equations to find the unknown value of the internal rate of return. So you can see there's many different ways to do it, and that's a beauty of engineering economies. There are so many different ways very often to solve the same problem. Isn't it awesome? So here, look, this is just basically net present worth is equal to 0. So if net present worth is 0, from that equation, if we find the interest rate I, then we found the internal rate of return. So here we have present worth of benefits minus present worth of costs, which is net present worth. Alternatively, we could find the ratio of benefits versus cost, present worth of benefits versus present worth of cost. And when it's 0, at that interest rate, we got the internal rate of return. As I said, net present worth, because this is exactly equation of net present worth. Or we could also look at it from perspective of uniform series, and then we can look at equivalent uniform annual worth, which is simply equivalent uniform annual benefits minus equivalent uniform annual cost. Or another equation is present worth of benefits equals to present worth of costs. Now let's take a look at this example of rate of return calculations. An engineer invests 5,000 at the end of every year for a 40-year career. If the engineer wants 1 million in savings at retirement, what interest must the investment earn? So the way to approach this problem is we need to look at the question, right? What interest must the investment earn? So what we're really looking for is the rate of return. What's the rate of return if the engineer will be investing the money? So how does the engineer invest the money? He invests 5,000 at the end of every year for 40 years. So that shows that we have the same amount for 40 years invested each year at the end of each year. So that shows that we have a uniform series. So we have this uniform series from year 1 through year 40, and this will be deposited in the account, and then so that would be the cost to the investor, and then he would get a benefit at the end of this 40 years of 1 million. So that's a single payment. So if you were to look at this from the way of cash flow diagram, then we would have the benefits, the expenses of uniform series as structured as the uniform series at 5,000, and then at the end a future amount of 1 million, and that would be a benefit. So then what we need to do to find the rate of return is we need to find the present worth amount or annual worth amount for that would be 0 at the interest I. So we need to find the value of interest I that would turn the present worth or annual worth of all these payments that we just described into a 0. So setting this up, we would get net future worth, and again, it doesn't have the present, it could be a future worth, right? If we just need to focus on a single time and turn all of the values into the single time point. So we're looking at net future worth, which is all the future costs, all the future benefits minus the future costs. So as I said, from the investment standpoint, the 5,000 is the cost to the investor, and so this is negative 5,000. And this is a uniform series. We need to find its equivalent future value. So to find the equivalent future value, we multiply this annual amount by the discount factor f given a. And again, we don't know the I. That's what we need to find out. We don't know the I. We know that we have these payments of 5,000 over 40 years. So this is n equals 40. And then 1 million is at the end of the 40 years. So it's right already at the end of the year. So it's already a future amount. So again, even though we didn't see this equation in the example, it's basically the same thing as if we had a net present worth equal to 0, or net annual or equivalent uniform annual worth equal to 0. So again, right, setting it up, it's easier this way, but equivalently, we could set it up as net present worth. We would just need to set up a different equation. Specifically, if you needed to set up the equation there, the equation to set up would be the following. We would have, again, right, we would have this cost of 5,000, but then we would look at this cost of 5,000 because it happens every time, right? That would be some annual amount there. We would also have this future worth of future amount in terms of benefits of 1 million. So then we would set up the equations there to find net present worth rather than net future worth. We would look at this again as the annual. We would want to find the equivalent present value of these money. So it would be P given A at I 40 years. And we would have this as well. This was a positive because it's a benefit. But that's still a future. If we set up a net present worth equation, then we would have wanted to translate this amount into present sum or discount it back to the present. So we would find the present value of this given the future at interest I over 40 years. And again, set this to 0. So as you can see, this is a different equation. This equation is different than this one. In terms of, but whether we using this equation or this equation, we would still get the same value of I. This one is just simpler because rather than having two discount factors, we only have a single discount factor. So whenever possible, we would prefer to have a single discount factor rather than multiple discount factors because it simplifies the calculations. When we have two discount factors, it's you would need to use some kind of numerical computations to solve for I. But if you have a single discount factor, it's easier to solve for I. So that's the reason why we wanted to set up a net future worth rather than net present worth. Alright, so we're going back to this equation of net future worth. We set it up, we set it to 0. From this, we can solve it for I. So again, that's the same as if we just move this part to the from the right hand side to the left hand side, then we would have 5,000 multiplied by f given a equals to 1 million. So then we can just simplify by dividing both sides by 5,000, and then that would give us f given a equals 1 million divided by 5,000, which would be just 200. And that's exactly what we have. So now 200, that's our discount factor. Can we find an I that such that f given a I at 40 would be 200? We can look in the tables in the book and look at different pages for different I and look into a column f given a and row 40, and we can see that in those tables at I equals 7%, f given I 7% 40 is very close. It's actually 199 and 636. So approximately, if we approximate it, it would be 200. Therefore, we can conclude that the required rate of return is approximately 7%. All right, another example of the calculations of rate of return. So if you have these cash flows where we have negative 700, and then we have benefits 100 the first year, 175 the second year, 250 in the third year, and 325 in the fourth year, we can notice that every time the difference between the first year and the second year is 75. Between the second year and the third year is 75 again, and between the third and the fourth year is 75 again. So what it means is that it's increasing, the benefits are increasing by $75. So we have a linear trend. So we would have a gradient series. So the linear trend increasing, and we have arithmetic gradient series, right? Do not confuse it, of course, with exponential. In exponential, it would be a rate. They would be increasing in a constant rate, not by a constant amount. So we have this arithmetic gradient series. We can look at it from the standpoint of equivalent uniform annual worth. So we're setting up the equation for the worth, setting up to 0, and of course that's the benefits minus the cost. And why we set it up like that? Because again, right, there's this annual amount that we already have. So that's 100 that is already annualized, that we don't need to do anything to. But we need to change the 75, which is a G, into annual amount by multiplying by discount factor, and change the 700 into its annual amount by multiplying discount factor A given P. So from that, we can actually try different I equal 5%, we get plus 11. At I equal 8%, we get minus 6. But at I equals 7%, we get exactly 0. So the answer is the rate of return is 0. Here's another example of rate of return calculation. Maria borrowed a student loan of $9,000 each year for 4 years. No interest is charged until graduation. Then the interest rate is 5%. If Maria makes 5 equal annual payments, what is each payment? And also, what is the internal rate of return for Maria's loan? So we're going to start first with finding the annual payments, the amount of annual payments. And of course, we want to draw a cash flow diagram for this example. And then after we find the annual payments, then we'll look for rate of return. So notice that Maria borrowed a student loan of $9,000. The $9,000 was used to pay a tuition for the year. So the tuition was paid at the beginning of the year. Because we have the end of the year assumption, that means that we need to move, not really move, but consider this payment at the beginning of the year as the payment at the end of the previous year. So she would pay $9,000 at the end of year 0, or at the year 0, and then she would pay another $9,000 at years 1, 2, and 3. And so at year 0, she would pay for the first year, and then at the end of year 1, she would pay for the next year, which is year 2, and then at the end of year 2, she would pay for year 3, and year 3 she would pay for year 4. So again, that's how it works. So we would have these cash flows, the negative cash flows, because that was the cost of 9,000 at the points of years 0, year 1, year 2, and year 3. And then she would pay the loan at 5 equal annual payments. So starting year 4, she would use that, and she would not have to pay it until the end of year 5. So starting in year 5, we would have 5 equal annual payments. So it would be at the end of year 5, also year 6, year 7, 8, and 9. We would have these 5 equal payments that represent the repayment of the loan. So she would get the 9,000 at the beginning of the year, but then she would pay it back at the end of the year. So that is how we have the cash flow diagram. So let's go ahead and draw it. So we have 9 time periods, which each represents year. So here we're gonna get, since she's getting a loan, I might have said it pointed downwards, it should be pointing upwards. So should be pointing upwards. In year 0, 1, 2, and 3 she's borrowing, and then she's paying back, so that's a cost of 5, 6, 7, 8, and 9, arrows pointing down. That's exactly what we have. This is her borrowing 9,000 at the beginning of the year. Therefore, we look at this as the end of the year, previous year. And then she's paying back at the end of each year in equal amounts. So here's a uniform series of her paying it back. So of course, she didn't have any interest during the year 0 all the way through the end of year 4. And so because an interest is 0, that's the same as just adding all of them up. And so here at the end of year 4, she owes 9 times 4 or $36,000 in loan. So she needs to pay back $36,000 worth in loan. So this should be an equivalent amount to paying $36,000 in loans at year 4, but at the interest rate of 5%, right? Because here, starting year 4 and all the way to the end of year 9, we're using interest of 5%. So that's gonna be, we can find the A given the present amount of $36,000. We can find its equivalent uniform annual cost, right, for the cost of $36,000 that has to be paid back at the end of 4 years. And so we use the to find the A, we're using P, find A given P discount factor. So we're gonna multiply 36,000 by find A given P. And that's what we see, right? 9,000 times 4, this is 36,000, that's accumulated by the end of year 4, and then discounted because this is a present with respect to this uniform series. So we know the present, we want to find the annual, its annual equivalent. So A given P, A equals P, A given P again, repeating itself in the same order. And then at 5%, because that's the rate that we're using during these years 4 from the end of year 4 to the end of year 9. And there's 5 years because the 4 is going to be the new 0, the 5 is going to be new 1, the 6 is going to be new 2, 7 is going to be new 3, 8 is going to be new 4, and then going to be the new 5, right? And in fact, from 9 subtracting 4, we're gonna get 5. So 5 years, and you can see here 5 equivalent uniform amounts in the series. So that evaluates to $8,316, and that's this amount here. So now what we want to do is we want to find, now that we found the amount of each payment, now we want to answer the second question, and that means we want to find the rate of return for this loan. So now in this case, when we look at the rate of return, we don't have two different interest rates of 0 and 5. Instead, we want to find a unknown common interest rate that would be from 0 to 9. So this rate of return means that we would have one single interest rate from 0 to 9. That's our rate of return. So we're going to set up the equation and set the net present worth equal to 0. So to set the net present worth equal to 0, we first look at the values here, right? So 9 is already present, but these 3 payments are uniform series. So we have net present worth, which is benefits minus cost. This is a benefit, so we have 9,000, it's already at present. And then we have uniform series of 3 payments that could be moved to the present, right? Directly to the present. So that would be A multiplied by the factor of P given A, because we're finding the present equivalent of this uniform series. So we want to find P given A. So multiply this 9,000 is going to be multiplied by P given A at 5% over 3 years. And then we also have these A that we just found. The amount A is 8,316. So these payments, we can move them all to the future, or we can move them here, which in both cases it's going to be future amounts. So if we're moving them to 4, right, we can't really move them to 0 immediately, because the structure of uniform series is that they start in the next period, right? So they start after 0, the next one is going to be 1. So we can only move it here, so the uniform series can only be moved to the 4. Or it can be moved to the 9, but let's move it to the 4. So the 4 with respect to uniform series will be present, so then we multiply this 8,300, right, or our A will be multiplied by the P given A, and that moves them to 4. But then again, with respect to 0, the 4 is the future, so we need to multiply it again by another discount factor just to discount it all the way back to 0. And when we already get this, then we'll get a single that's going to be representing a single future amount. So the second discount factor we will multiply it by is going to be P given F. And we discounted 4 periods back, so it's going to be P given F at I over 4. So that's exactly what we have. We're setting up net present worth equals to 0, because that is the equation from which we're going to determine the rate of return. And then this is 900 in the present. This 9,000 in the present. This is 9,000 that represent this uniform series. And so it's multiplied by the discount factor of P given A over 3 periods at the internal rate of return I. That's the rate that we need to determine. And then negative, because these were the benefits, there was plus. The A is negative because it's a cost to us. Negative 8,316, that's the amount 8 here. And we first move it to 4. And this is discount factors that allows us to move it to the time period 4, and that's P given A, because this is going to be present with respect to these, right? I, that's our rate of return over 5 periods, but that's just going to appear here. We can't sum it up to the rest of the present values, so we need to discount this future amount with respect to the present. And so we multiply it again by another factor of p given f at I over 4 because we're moving it 4 periods, 4 years. So now that we understand this equation, next what we want to do is to solve this equation. Notice how involved this is, right? We have multiple discount factors. That's what makes it hard. These multiple discount factors. What we can do is we can try different i's. So I suggest that we try these i's. We can try 2% and we can try 3%. At 2%, when we plug 2% instead of the I, what we're gonna get on this left hand side, we would get minus 1251 rather than 0. If we plug in 3% on the left hand side rather than 0, we would get $620.50. So this is a positive one, this is a negative one. That means that somewhere in between we would have a I that would turn it to 0, right? If they both were negative, then we would try to continue increasing, right? And let's say this would be a negative number, and this would be a slightly smaller negative number. We would try to increase here. If it was the other way around, this would be the larger numbers, and we would have to go back this way and start decreasing 2%. But either way, we would try to go and find the two percentage points at which one is positive and one is negative, and that would mean that somewhere in between this net present worth curve is going to cross 0. And so then if we found those close interest rates, then we can use linear interpolation. So let me show you how to set up the equation for linear interpolation. So this is how we could set up the equation. We could consider that the ratio would remain the same, right, in terms of the argument to the to the function, right? So if the net present worth is a function, and we consider its argument, the difference of the arguments to the values of the function should be the same, right, for different values of the argument. So now we have I minus 2% difference divided by the differences of corresponding net present worth of I minus the difference in net present worth of 2%. And that's going to be the same as if we basically set up the same percentages here, right? So the difference, I'm going to copy this. This is going to be a difference here, and this is going to be the difference here, right? If we plugged in the 3% here or any other percentage, that would actually work exactly how it should. So you can see, right, that for I, the ratio of the argument to the function value is the same as the difference of the arguments to the difference of function values for 3%. Plugging in 3% here. And so then we could use this and plug in the values of the formula. So let me copy the formula real quick, and then plug in the values. So the values of I, we don't know. We know that net present worth of I is 0. So instead of this, we're going to plug in 0. Instead of net present worth of 2%, we're going to plug in negative 1251. And so if we plug in the negative 1200, then it turns this negative into a positive. So plug in negative 1251. And then here, instead of net present worth of 3%, we're gonna have 620 and a half, And then again here, instead of negative 2%, we're gonna have negative 1251. And so this again, right, this can be simplified further, and so this is going to be a plus here, and then again this is going to be a plus here as well, instead of the minus. And so this is just going to be a 1%, and then adding, or we could rewrite this simply as so 625, and then 620 and 0.5 tenth plus this 1251, it's just gonna be here 18, and then 71 and a half, and then 1%, and then this 1251. We could further simplify this, right? So after, let's do it a little differently. So let's do it slightly differently. So now I can just move this 1251 up here by multiplying both sides of the equation by 1251. So let me just copy as this. So I'm going to multiply this by 1251. To denote multiplication. So if you multiply it here, then all we have left is just I minus 2%, I instead of t. And then this 2% I can move to this other side by adding 2% to both sides. So adding 2% to this side and 2% to this side. This just gets rid of both of them. We only have I in this case, and then we can simply just divide 1251 by 1871 and a half. So using a calculator to divide 1251 divided by 1871 and a half, I'm gonna get something like this. So that's gonna be our I. So I is gonna be 2% plus, notice there is a percent here, so this is gonna be in percentage points, so 0.6 and approximately 7 or 668. So that's approximately 7. And that's going to be 2.67%. And this is how we got this. So again, right, you can see that we started here with setting up this equation for linear interpolation, and then we solved the equation getting 2 0.67. And that's exactly what we get here. Using a linear interpolation, we obtain the interest rate, which gives us an internal rate of return, because that's the one that gives us net present worth of 0. All right, so this example was very useful because it shows that we can have different interest rates, and then we can combine all the cash flows together through time to find the internal rate of return, and that gives us a single rate of return throughout this entire loan. So again, if you look at the rate of return in a student loan, this is what it was as the amount owed at the start of the year, and at interest of 2.66, which is pretty close to 67, right? We're gonna get the interest on this loan. Then this is the cash flow at the end of the year. We have the amount owed at the end of the year. So remember, we again getting another loan to pay for the next year. So we adding this together, and we adding the interest rate, and that gives us amount owed at the end of the year. So this amount carries over because the end of the year is also the start of another year, next year. So we have this at the beginning of the next year. It accrues interest of 2.66. So that's just multiplying this 18,000 something by the 0.0266. We'll get this. And then again, we pay, we getting another loan that we will have to pay off later. So we're getting this another 9,000. So now it increases the amount right to, so we have this value, we need to add the interest, and we need to add another additional principal that is added to the loan. So we get this much, and that carries over, and so on. So up to this year, where we're not borrowing anymore, but we are stuck with this amount. And so this amount right now, we're gonna start paying it back. So we calculate the interest on this amount, and that's gonna be this much, and then we're paying it back in these equal payments. So then this is the amount that we will have to pay it back by, and so it reduces the amount owed. So we're subtracting these two, that gives us this amount, and that's what we have at the beginning of the year. Again, if you computed the interest, that's how much we have in terms of interest paid on this. This is just simply multiplying this value by the percent rate, and then we'll get this cash flow as always, because this is the amount that we pay each year. And so here's the amount owed, is basically we're subtracting this amount from the amount owed at the start of the year, and so on. If we continue, we pay off the loan in full. So if we plotted these values, that's what we're gonna get in terms of net present worth. We're gonna get net present worth of this, and you can see that, interest rate, right, is approximately, right, somewhere between 0 and 5%, approximately 2.67. So we can also plot a net present worth versus interest rate in terms of borrowing case. So if we look at it as a borrowing case, we borrowed some amount of money and then paid it off, the interest rate curve would actually look just like what we saw in the previous plot. So the net present worth is going to be the vertical axis, and the interest rate is going to be horizontal axis. We're going to see something of where we have the net present worth from the negative net present worth increasing to the positive in this concave fashion, and somewhere here we're gonna get internal rate of return And if you look at it from the borrowing perspective, right, so the opposite perspective to the lending perspective that we had before, we could have a borrowing perspective or investment perspective. So now we're looking at the from the instead of borrower perspective, we're looking at the lender perspective or investment perspective. So here we're investing some cash flow, so this is a cost to us, and then we're getting the benefit. So again, we can plot net present worth in this case, and in this case, it's gonna start with a positive, and then gonna reduce in the convex fashion. So again, net present worth as the vertical axis, and then we have the interest rate, and then we're going to start somewhere here at interest 0 as positive, and then it's going to be decreasing towards the negative. And that makes sense, right? Because as due to the time value of money, as interest increases, this earlier cash flow starts to have a much larger weight. If the interest rate is becoming larger, the time value of money makes this into a more heavier discount, right? And these are heavier discounted compared to this negative cash flow. So that's the reason why it looks like that. Versus the previous case, it was the other way around. The signs were the opposite. All right, so this is useful. Keep in mind when solving the problems, keep in mind what perspective you have and whether you start with negative cash flows and then have the positive benefits, or the opposite if it's a borrowing case and not a investment case or lender case as we see in this slide. But if it's a lender case, a borrow case that we saw in the previous slide, when we start with a positive P and then have some costs, so first the benefit then the cost, then it would be the opposite. So keep that in mind, because you want to know, right, whether it's going to be increasing interest rate or decreasing interest rate, and which way to go, right, to find the different I's, right? If you got some negative one here from the borrowing case, then you're going to be increasing the I to try to find the positive ones, and then you'll interpolate in between. In this case, right, you're going to do the opposite. When you have the lender's perspective and you start with a negative cash flows and have some benefits, then you'll find maybe some positive one at a smaller rate, and then you will try to increase I to find the negative one. So let's take a look at this example. This is an example of rate of return calculation. We have a new corporate bond that was initially sold to an investor for $1,000. The issuing corporation promised to pay the bondholder $40 interest every 6 months and to repay the $1,000 face value at the end of 10 years. After 1 year, the bond was sold by the original buyer for $950. First question is, what rate of return did the original buyer receive on this investment? So we're gonna plot this. This is two 6 months periods. So we have two time periods that represent a 6 months, because of course, remember, we get interest payment every 6 months, and then at the end of the first year it was sold back. So first we bought it, right? So by buying the bond, if you take the perspective of the buyer, right, from the buyer perspective that bought the holds from the bondholder perspective, the bondholder had the cost of $1,000, so that would be a negative 1,000 here, and then would receive the benefits of $40,000 here, not $40 here and $40 here, and then also have another benefit from selling the bond for $950. So on top there would be another single payment. These would be the series, and then we would have a single payment. And we want to know the rate of return that the original buyer received on this investment. So first we'll find the effective, what we want to find here is actually effective 6 months rate, and then convert this effective 6 months rate, because the time periods are semi-annual time periods, 6 months periods. We're gonna find effective 6 months rate and convert its effective 6 months rate into the effective annual rate. All right, so now let's draw a cash flow diagram. Just like I said, these are cash flows, and then we set up the equation for the defines the rate of return. This would be present worth of cost to present worth of benefits. Keep in mind, as I said, we're gonna first find the effective 6 months rate. So the I that we use here is gonna be 6 months rate. So we have present worth of cost. The costs are here. They're already in the present, so we don't need to multiply it by any discount factor. So it's just 1,000 in the cost, and then it's equals to the benefits. And so we have 40 as a benefit, uniform benefit. So that's A. We need to find its present equivalent. So find P given A. So multiply by discount P given A. At the interest, 6 months interest I, and then over 2 time periods, and plus the single payment of 950. So it's a future with respect to the present. So 950 is going to be multiplied by discount factor of P given F, because we're finding the present of some future amount, present equivalent value of future amount. So 950 multiplied by P given F, I over 2. So now that we set up the equation, we can find the I, again using interpolation. We can try also 1.5%, and it actually gives us very close, so we don't even need the interpolation. We can get the present worth of benefits, plugging in this 1.5 here on the right hand side. It gives us, evaluates to $1,000.41, which is quite close to the 1,000. So we're gonna see that 1.5 is our 6 months rate here. So that's effective 6 months rate. We again need to find the effective annual rate from there. So there's 2 time periods. So it's gonna be 1 plus 1.5 to the second, and then minus 1. So that's exactly what we get. In terms of a nominal interest rate, we'll have 3% nominal rate, and an effective interest rate is 1. Again, this nominal interest rate is yearly rate, so 3%. However, it's not the effective rate. The effective rate is found using this formula, where we have 1 plus this 1.5%. Remember, this is a percentage, so this 1.5% is the same as 0.015 thousandths, and then to the second, because that's how many time intervals we have in 1 year. So to the second degree, and then minus 1, and that gives 3.02%. So the rate of return, annual rate of return, is 3.02% effective rate. So now the second question for this problem is, what rate of return can the new buyer expect if that buyer keeps the bond for its remaining 9-year life? So if it's 9-year life, then we actually have a 6 months period, 6 months period. So those semi-annual time periods means that we need to multiply 9 years by 2, so we'll actually get 18 remaining periods, and that's what you see in the timeline here. So we can draw a cash flow diagram. So the buyer bought it, the new buyer bought it for $950. So that's the cost to the buyer, negative arrow pointing down, of $950, and then the $40 that the new buyer gets every 6 months. So we're gonna get this uniform time series, and then there's gonna be a face value paid back for the bond, $1,000. So that's gonna be a future amount, future benefit amount. So in fact, we have 950 pointing down, then we had those $40 annual, actually not annual, 6 monthly payment, and an additional face value of the bond payback at the end of 10 years, right? Because that's the remaining 9 years. It's the end of the 10 years. So again, setting up the equation for I, and again, this is we're gonna be using effective semi-annual, which means 6 months interest. And so this is the present worth of cost. The rest is benefits. So again, 40 multiplied by P given A, because it's uniform series, over 18 periods in this case. And then again, this 1,000 happens at 18 periods, and that's a future amount. So it's multiplied by P given F over 18. And so in similar fashion, we can plug in different values of I and then compare them to this 950. So when we try 5%, the present worth of benefits is going to be underneath the 950. It's going to be $883.10. So you can try. So again, right, this is the perspective of an investor perspective or a lender perspective. So if you recall, the way we had the plot there is that we started with the positive and then it would become negative. So if we tried 5%, then we need to try, and it was below, then we need to try a smaller I to try to get the larger benefit. So we try in a smaller I, and the smaller I is 5%. So again, how did I find it? I looked at the plot. Right? Why did I thought right away that it's smaller? I looked at this plot that we looked at here. Right? We first paying something and then we realize some benefits. So it's reducing. So if we got benefits that are smaller, remember the net present worth is benefits minus costs. The benefits for 5% were smaller than the costs, therefore the net present worth would be negative. So the 5% would be somewhere here, and so I would need to reduce the I, and that's what I did, and I tried 4% and I got a positive. And so that's what we have here, right? We set it up, we plug in I 5%, we got negative net present worth, and here for the 4% we got positive net present worth because the benefits exceed the cost. And so that's how it expected, right? So we have this crossing the horizontal line, the net present worth would cross the line somewhere between 5% and 4%. So what are we going to do? We're going to interpolate. So again, it's the same way like we did before. We're going to set up the equation where we have two ratios, ratio of the difference of i's to the difference of net present worth. And so by interpolation, we can get this internal rate of return of 4.43%. I'll leave it up to you to set up the equation just like I showed earlier to get this value. All right, so then keep in mind this internal rate of return that we found is a semi-annual effective rate. So from that we can find the nominal rate simply by multiplying by number of semi-annual periods in a year, which is 2. So multiplying by 2 we get this, pretty clear. And then effective rate is found from that equation where we have 1 plus this percentage to the second degree because there's 2 semi-annual periods, and then minus 1, and that gives us a larger percent. That's this nominal rate, which is not surprising, right? This is our effective annual rate of 9.05%, and that's the answer to the question, what is the rate of return? The effective annual rate is 9.05%. So now here's another example. if or continuing this example 7.5, if the issuing corporation paid a 1% fee to sell the bond, what is the effective interest rate that the firm is paying on the bond? So keep in mind, right, the issuing corporation paid 1% fee to sell the bond. So whatever they sell it for, they will reduce it by 1%. So again, we're setting up the equation of net present worth of benefits minus costs. That should be equal to 0. And so we sold it, or issuing corporation sold it for 1,000 minus 1%. 1% of 1,000 is $10. So 1,000 minus $10 is going to be 990. And then they also paid, so that would be what they received as a benefit, and then they would pay $40 every semi-annual period for 10 years. So there's 20 semi-annual periods in 10 years. So we're turning this cost into present cost. This is a uniform series. We're turning them into present cost, so multiplying by P and A. Very similar to the previous examples. The only difference is going to be over 20 time periods. And then this $1,000 is a future amount. It's a cost, of course, so it's negative. Future amount that is going to be paid by this issuing corporation at the end of the 10 years, which is the end of the 20 semi-annual periods. And so PGMNAF 20, right, is a discount factor. So again, what we're going to do is we're going to try different I's and find the I's that will give us a negative, the close nearby I's or interests that each would give us, one would be a positive, another would be a negative. So what we can try, well, we can try first 4.5%. At 4.5%, we get $55.08 of the net present worth. So it's a positive. So now we want to find the negative one that's close to 4.5%. And so what we can do here is, again, we will need to think in terms of whether we're going to go up and increase interest or whether we're going to decrease interest. Right? So keep in mind that here we are, as the issuing corporation, first has the benefit and then has the cost. So rather than that second plot, we're actually looking at something like the first plot that we saw. So let me show what exactly we see, and then that will tell you that we actually going to have, right, because it's going to start going like this from the negative to the positive. So because of that, it's going to actually be a, we will need to find the, we will also need to decrease, because we found the positive, we need to decrease to find the negative in this case. So let me show you real quick what I'm referring to when I'm talking about the plot. So keep in mind, right here, we first had the benefit, then we had the costs later. So that is the plot that I'm referring to, right? First we had the benefit from selling, issuing corporation had the benefit from selling the bond, and then they had to incur costs paying the coupons and then paying the face value. So we had something of this nature. So that would be the plot of the net present worth. So when we got something positive here, we needed to find something negative. The negative would be found by decreasing the I. We would find the negative. And so we had a 4.5. We would need to decrease this percentage to find the negative. And so that's what we're going to do. So as I said, right, at 4.5%, we get this positive value. We're going to decrease it, decrease interest rate from 4.5 to 4, and that actually gives us a negative, slightly negative value of negative 10. So they're close. These two percentages are close nearby. These are very close. So we're gonna use a linear at this point. We can use linear interpolation. Using interpolation, we would get the rate of return, internal rate of return of 4.77%. Are we done? Yes, I heard you. You're correct. We're not done because this is only an effective semi-annual rate because we used these semi-annual periods of 6 months. But now we need to find the nominal and effective yearly rates. So the effective yearly rate is very simple. As you remember, we just multiply it by 2. However, we want to find the effective rate. So the effective rate is 1 plus, right, this 4, a little over 4%, and then squared because we have 2 semi-annual periods minus 1. So that gives us 8.32%. And so this concludes that example. And we have another example. Here we have two options to acquire a property priced at $300,000. You can either finance through the seller was 20% down and the balance due in 5 annual payments and 12%, or we can pay cash with 10% discount. So the question is, what is the internal rate of return for the loan offered by the seller? So let's take a look at the first option. So the first option is we have this 300,000 that will have to be financed, right? But not the entire amount. We have to pay 20,000 out of this. So we're only financing the remaining 80% of the 300. So therefore, we multiply the 300,000 by 80% because that's the amount we're gonna finance, and we want to find the annual payments. So that's gonna be, that was a present worth, so split into uniform series, so it's going to be A given P at 12% over 5 annual payments, so over 5 years. And so plugging in the discount factor and multiplying these, and then multiplying by discount factor, we're going to get this amount, which represents our annual payment for the first option. So the second option, we also going to find annual payment for the second option. And then to find the internal rate of return, we set the equivalence relation. So again, net present worth of paying cash versus net present worth of finance. So paying cash was 10% discount. Right, so what we're gonna have, if we pay 10% discount, the 10% of the 300,000 is $30,000. So 300,000 minus the discount, 10% discount, would be $270,000, and that's our present amount that we would pay if we paid cash in full at the beginning at 10% discount. So that's already in the present, so we don't need to discount it. So we have that versus finance. You have to pay 20% down. 20% of 300,000 is what? It's 300,000 multiplied by 0.2, so that would be $60,000. So we pay $60,000 at present, so that's what we have, that's the cost of 60,000. We don't need to multiply by any discount factor because it's already present. And then we finance it with these equal payments. So uniform series need to be discounted back at our internal rate of return, right? So we can't use the 12% right here using internal rate of return. So we discounted into the present terms this annual payment at the present by giving by saying P given A I at 5%. Right, because otherwise, if you looked at it incorrectly, then that would be just 300,000 here. So you would think that financing would be the worse than paying cash. But either way, right, we need to find this internal rate of return to figure out the rate of return for the loan offered by the seller, because we're actually comparing paying cash versus the financing. So now, what is the rate of return offered by the seller? We simplifying, right? So moving this things around, we simplify it and find the P given A. So the P given A is 3.154 thousandths. And so then we can plug in different values of I, 15% and 8%, and these are close nearby, and this is right between these two. So then we can find, by interpolation, we can find the I that's somewhere between 15% and 18%, and specifically through the interpolation we can get that it's 17.6%. That's our rate of return offered by the seller. So now let's take a look at another example. We have two options to buy parking permit. Buy annual parking permit on August 15th at $180, or buy semester permits on August and January 15th at $130 each. Again, what is the internal rate of return for buying the annual permit? So to set it up, we're setting up whether we're gonna do a single payment versus the net present worth of the two payments. So this is how it would look. Alright, if we had a single payment, we would pay it in August, and then the January, right, we still include the January in consideration, versus the two we have in August 130, and then in January another 130. So then, right, if you notice, there's actually 1, 2, 3, 4, 5 months till January. So that means that we have 5 time intervals. So subtracting the two, right, we can find the incremental cash flows. Incremental cash flow would be we subtracting it from the single payment, we subtracting the two payment options. So these, we only can subtract the cash flows that happen at the same time period. So this 180 in August versus 130 in August for the two payments option is going to give us $50, right, negative cost. And then this is going to be a positive because, again, we're subtracting the negative gives us a positive 130. So that's how we got the these benefits, right? So this is incremental benefits from paying in full in single payment. So the net present worth of annual payment versus net present worth of semester payment, we can also set it up like this. And again, it would simplify in the same exact manner. So moving this here would be negative 50. Moving that also to the left-hand side would be positive 130 equals to 0. So from here we can determine the effective monthly rate of 21 and 0.06%. So annual effective rate we can find from there. You plug in this in, and notice we're taking it to the 12th degree because there's 12 months in 1 year, so 12 compounding periods, and that gives a huge interest rate of 891%. So of course paying off, this is a huge percentage, so paying off at the very beginning is beneficial. So now another example, two options to pay liability insurance. We can pay quarterly at $10,000 per quarter, or you can pay annually at $35,000. So what is the rate of return for paying on an annual basis? Again, annual basis is a much better deal. We have 4 quarters, therefore 4 different time periods. We pay it at the beginning, so at time 0 we pay 35, versus paying quarterly at the beginning of each quarter. So we get this type of cash flow diagram because, again, remember, we pay an insurance, the insurance payments. If you remember, I mentioned that during chapter 2 that the insurance payments we would pay at the beginning of each time period. So we pay at the beginning of year 1 for the entire period, year 1, and then again at the beginning of year 2, which is the end of the year 1, we're going to pay for the year 2 and so on. So that's how we pay, and this is the cash flows for the two options. We can set up the incremental cash flows by subtracting from the annual. We're subtracting the quarterly. Typically we always subtract from the first larger initial cost. So we're subtracting from this 35, negative 35, we subtract negative 10,000. That leaves us negative 25, right? The arrow pointing down was a 25. And then subtracting these 10,000s during 1, 2, and 3 will get us minus, and minus is going to be a plus, so we'll get us positive benefit of 10,000. So when we pay net annually, we have a benefit of not paying these $10,000 during the first quarter, second quarter, and third quarter. Incrementally, right, it's only 25,000 that we pay on top of the 10,000 that we already would have paid anyways. So again, setting up the equations, net present worth of annual versus net present worth of quarterly payments, we'll get the 35, which occurs in the present, so it's already in the present, no need to multiply by any discount. And this 10,000 also occurs in the present, so no need to multiply by any discount factor. But these payments, right, are uniform series, three same payments, annual amounts of 10,000. So we need to find their equivalent present value. So we multiply it by the factor P given A, because we're finding the present value of this A. So P given A, I is going to be a quarterly interest rate, and during 3 quarters or over 3 quarters. So now from here we can simplify, right? We can move everything on this side, then that would decrease this 35, negative 35 to the negative 25, and that would be with a positive. So it's the same as if we use the incremental. So we could have just set the incremental and then set the net present worth and incremental equal to 0. That's an alternative way to do it. Either way, we can simplify this to find the P given A. The P given A is going to be the 25,000 divided by the 10,000, and so that would be 2.5. So the P given A is 2.5. We can try different interest rate. So trying 9%, we're going to get 531 thousandths. That's pretty close, but when we try 10%, we're going to decrease it. So it's going to be 2.487. So again, why did we try the 10% after trying 9%? Well, again, we have the negative and then we have the benefits. When you look at it from this perspective, we have the negative, then we have the benefits of when we pay annually. So again, that's the same thing as we had in the first example. So it would be increasing. So if we had something, or actually decreasing. So if we had something at 9% that is a little larger, then going less to 10% is going to be this smaller, gives us a smaller P/A. So now what we need to do is just set up the linear interpolation. So the linear interpolation is again set up as the two ratios of the corresponding differences of I minus whatever the percentage we choose, for example 9%, and then P given A for the I, which is 2.5, minus P given A of 9%, which is this much, and then it's equals to the the ratio of the same kind of ratio, but instead of I, we're going to plug in the 10%. So 10% on top is the difference of 10% and 9%, versus at the bottom we give the difference of P given A at 10 and P given A at 9. And so doing that, you can establish that in a quarterly effective interest rate is 9.705 through the interpolation procedure. But that's a quarterly rate. What we also need to find is the effective annual rate. So effective annual rate is found by this formula, where we're using the fourth degree, using this quarterly rate as effective quarterly rate, and then we're using the fourth degree because there's 4 quarters in a year. And so again, don't forget to subtract 1. That gives us 44.8%. So you can see this is a huge percent, telling us that it's highly beneficial to pay annually, because that gives us this percent, 44.8% versus paying quarterly. Here's another example of rate return calculations, whether you want to buy or lease option for 2 years. If you buy equipment at 40,000% with salvage value of 6%, or we can lease equipment of 2,500 per month. What is the internal rate of return of the lease? So we set up the equation of buying versus leasing. So here, this is our buying, right? We have 4,000. We bought it. This is our cost minus 40,000. And then the salvage value is going to be a benefit. It's going to be at the end of 2 years. So 6,000. And we're looking at the effective monthly rate, because we are leasing the equipment each month, finding effective monthly rate. So during 2 years, it's going to be 24. So this 6,000 happens. The salvage value benefit happens at the end of the 24th period, because again, 24 monthly periods in 2 years. And then for the lease, we pay in lease at the beginning of each time period. So again, it would be paying the first month's lease at time 0, and then the all consecutive ones at the beginning of each month rather than the end. So that means we have this 23 additional payments. So that's the uniform series, so we need to find their present force. So P given A here. And so then we could, again, simplify some of this by moving things around and then plugging in the different I. So that's simplification now by moving this 2,500 positive with a positive sign to the left-hand side. So then we can plug in different monthly interest rates. So if you find the value, if we plug in the value of 4% here and here, then we get 1,983, which is of course much larger than 0. Then we can try a larger rate here, and plugging in the larger rate, we'll get a negative 1,917. So these are between between these two, we're gonna have a 0, right? This is a positive, this is a negative. Between them, our value, our function, this function would be crossing 0. So somewhere between 4 and 5%, we're gonna have our interest rate, that is the internal rate of return, the interest rate that turns this to 0. So by interpolation, between 4 and 5%, and using these values, we're gonna have 4.51% as the effective monthly rate, from which we can determine the effective annual rate. So effective annual rate is, again, there's 12 months, so to the 12th degree, we plug in this percentage, which this is actually the value of 0.0451, and so that gives us a percentage rate of 69.8%. So that's a benefit of doing rate for or internal rate of return of the lease option. So now let's talk a little bit about incremental analysis. So it's important to learn this incremental analysis. So when there are two or more alternatives, the rate of return analysis is performed by computing the incremental rate of return. And that's also denoted as delta IRR on the difference between the two alternatives. The cash flow of the incremental investments is computed by taking the higher initial cost alternative and subtracting the lower initial cost alternative. And then if our incremental rate of return is larger than minimum attractive rate of return, then we're going to choose the higher cost alternative. If the incremental rate of return is smaller than minimum attractive rate of return, then we're going to choose the lower cost alternative. So again, why? Because here we're comparing it to the minimum attractive rate of return. Is the incremental rate of return gives us the desired benefit? As you recall, I mentioned that a company, right, or firm would typically have some rate of return that they want to achieve, right? So they want to achieve or exceed this rate of return due to their obligation to stockholders, or some other considerations in terms of the benefits, right? They want to realize some kind of benefit from, or some kind of profit, some kind of profits that they want to realize. If they want to see some type of growth and they want to establish the rate at which their invested money will grow. So this minimum rate at which they would, which they want to achieve, they want to either get that rate of return or higher rate of return. That is called minimum attractive rate of return. So if the incremental internal rate of return, incremental rate of return is larger than minimum attractive rate of return, then we would invest more money. But if it's smaller, then we would rather invest those additional money into something else that would give us minimum attractive rate of return or larger rate of return. So here's an example of incremental rate of return calculation. We have an equipment that can save $1,200 per year and has no salvage value at the end of 5 years useful life. We have two suppliers to go with. We can either choose LeaseCo, which offers 3 beginning of the year payment of $1,000 each, or we can do a SailCo that offers an option of one payment of $2,783. So the SailCo, right? This is the SailCo option. We have some cost, a single cost at the beginning of the entire period. At the beginning of the entire useful life of this equipment, and we realize the benefit of using this equipment at the benefit of $1,200 per year. So we can set up the equations for the incremental rate of return, but we first need to also draw the cash flow diagram for LeaseCo and then find the incremental cash flows. So this is a LeaseCo. LeaseCo requires the 3 beginning of the year payments. So beginning of the year means it starts with 0. Then that's for the first year. For the second year, it starts at 1, and then for the third year, it starts at 2. So these are 3 payments of $1,000, and then we have these realized benefits, just as we would for SailCo, from SailCo, because it's the same equipment, just from 2 different suppliers. So then we're going to subtract these two. Why we're subtracting SailCo from the LeaseCo? You're right, because I said in the incremental rate of return analysis, we're going to subtract the higher initial cost alternative. From that alternative, we're going to subtract the lower initial cost. Obviously, the $2,783 is higher cost compared to the initial cost of $1,000 at time 0. So it's always compared to time 0. That's your initial cost. So then we're going to subtract these. We're going to get incremental cost. Subtracting from 2783, negative 2703, we're going to subtract negative 1000. Negative and a negative are going to be positive, so it's reducing this cost of 27 to just 1783. So we have 1783, and then this 1000 is going to be a positive, and this 1000 is going to be a positive because minus, and then the cost also has minus, so it's going to be positive as a plus. But these are the same, the benefits are the same, so they just cancel each other. Therefore, you don't see anything here in terms of these blue benefits. So these are the incremental costs and benefits of sale com minus lease com. And so based on that, we can set up a net present force to determine the incremental rate of return. So we can set up the net present force. So this is already in the present, and these are the two equal payments. So that's uniform series over 2 years at interest rate I, right? The incremental rate of return. So now, right, this is 8%. How did we do that? Let me quickly mention this. Here we're just gonna set up that equation as I said. We're gonna set net present force of incremental is gonna be 0, right? So what's the net present force? Well, we have this 1783, and that's already in the present time. So that's negative, right? That's a cost. So minus 1783. It's already in present, so no discount factor. Then we have a benefit of 1000, but the 1000 here is actually a uniform series. We need to find its equivalent present value. How do we find it? Oh, I heard you were correct. We find it by multiplying by discount factor P given A of at I over 2, right, over 2 periods. And that's setting up the equation. So from that equation, right, we can get that our P given A I2 is going to be incorrect. It's going to be right, so moving the 1783 to the right hand side from the left hand side was a positive sign. We're going to get 1783 and then divided by 1000, so it's going to be 1.783. And so that's where, if you look up in the book at 8%, look in a column P given A and row 2, that gives us the delta, right? So here it goes. Delta IRR is gonna be 8%. Right, just looking it up in the tables, in discount factor tables, at the end of the book, you'll get the 8%. All right, good. So coming back to our example, right, that helped us determine the incremental internal rate of return. Here's another example. We have 2 mutually exclusive alternatives, and we have minimum attractive rate of return. We have the minimum attractive rate of return of 6%. So which of these 2 alternatives we would select? The first alternative and the second alternative. Notice the first alternative has lower initial cost, so we're going to subtract that alternative from the second alternative, which has higher initial cost. So subtracting these two, we're going to get, right, so instead of 20 here as a cost, or as incremental cost, we're going to only have 10, because 20 minus 10, which is a plus 10, is going to be minus 20 plus 10 is going to be minus 10. So here is a negative 10, and then here positive 28 minus 15 is going to be 13. So that's positive 13 here. So this is our incremental cash flows. So from incremental cash flows, we can set up net present worth. All right, and so we could get the internal rate of return. We can find also internal rate of return for each of the alternatives. This is internal rate of return for alternative 1 is going to be 50%, just looking at setting up the net present worth equation here. And then for alternative 2, if you set up net present worth equation here, we'll get 40%. And for incremental, we get the incremental rate of return of 30%. So notice all of them are more than 6%, and specifically the incremental rate of return of 30% is more than minimum objective rate of 6%. So which alternative should we select? Yes, we should select the second alternative, because, right, it gives us the incremental rate of return that's higher than the minimum objective rate of return. So if you're interested in investing more money to get the rate of return that's higher than minimum attractive rate of return. So the answer is select the second alternative, select the higher cost alternative, because the incremental rate exceeds the minimum attractive rate of return. All right, so here's another example. So if we looked at it from this perspective, right, that would give us the incremental, and that's for the borrowing rate, right? In the borrowing rate, that would be the opposite. And then if you look at this example of incremental rate of return for 2 devices, we can install a device to reduce the cost. It has no salvage value at the end of 5 years of useful life. And we have 2 options. Device A costs 1,000 and saves 300 annually. Device B costs 1,350 and saves 300 in the first year, which increases 50 annually. So what does it mean when we say increases $50 annually? You're right, we have the linear trend in these benefits. Therefore, we have what type of gradient? Somebody said we have geometric gradient. No, that's not correct, because this is an increase by the same amount, not it was the same rate each year. So it's actually and not the geometric but arithmetic gradient series. So in fact, we have arithmetic gradient series for device B, and just uniform annual series for device A. So then we can find the incremental. Of course, we're subtracting from the higher initial cost. Device B, notices is the option with the higher initial cost. Subtracting these two, we have 350 as initial incremental cost, and then we realize these benefits. So we only have the geometric gradient, because if you subtract this uniform series, the only that we have remaining is this geometric gradient series. So this is our incremental cost. We can set up the equation of net present worth. So this is already in the present with a negative. This is going to be the positive 50. It's a G. So the G is going to be multiplied by PU and G discount factor over 5 periods. Remember, even though there's only four gradient payments, that's actually the gradients always start in the second time period. So the 5 is the end that we use here. So again, this is what we set up, just like I mentioned, the net present worth setting up to 0. This is a negative 350, and then the positive 50 multiplied by p given g over 5 periods. And that leads us to p given g is 7. How did we get it? We just move this negative with the positive sign to the left hand side, and then divide it by 50. 350 over 50 is 7. So from this, we can find the I by interpolation. Plugging in 9, we get something slightly above 7. Plugging in 10% instead of I, we get something slightly below 7%. Not 7%, 7. Just value as 7 because it's discount factor, it's dimensionless. So then it's going to be something in between 9 and 10%. So we're using interpolation here, as we often do, and we get 9.45% incremental rate of return. So the question is, assume again that minimum attractive rate of return is 6%. Do we go with device B or do we go with device A? Yes, at 6% minimum attractive rate of return, we would go with higher initial cost alternative, which would be device B, because the incremental rate is higher than our assumed minimum attractive rate of return of 6. Alright, this is great. Next example. Here we have incremental rate of return computation for these two alternatives. We have machine X versus machine Y. Notice the initial cost is higher for machine Y, so we're going to subtract the payments or cash flows for machine Y. We're going to subtract from the cash flows for machine Y the cash flows of machine X. We have uniform unit benefits for both cases, and the useful life salvage value, that's the future amount. These are annual amounts, these are present amounts, and we have two different useful lives. So what does it mean? We need to use different ways to look at it, right? We can either look at it for the present worth, but then we would need to try to think whether we'll use the least common multiple or whether we use a planning horizon. But if we use the annual worth analysis, then we can compare apples to apples by simply comparing their annual amounts. So that's what we're gonna do. In this case, rather than using net present worth, we're gonna look at equivalent uniform annual worth. And equivalent uniform annual worth will allow us to compare the alternatives where the useful lives of the alternatives are different. Therefore, we're going to use machine X and machine Y. If we do the incremental rates for machine Y versus machine X, if we had the net present worth analysis, then we would use the least common multiple of 2 lives, right? So for machine X, we would need 2 cycles. The machine Y has 12, the machine X has 6, least common multiple of it is 12. And so the incremental cost would be like this. And setting up the net present worth, right, would be quite complicated. So here we have 500. Of course, right, if you want to do the annual worth analysis, you can easily do that one instead. So setting this up, we get the incremental cost with the net present worth. We have, notice, 50,000, this is our cost, or sorry, not 50,000, 500 is our cost. And then we have the benefits, the rest are the benefits for incremental cash flows. So first we get this 25, this uniform series, all the way throughout 12 time periods. So we need to find this equivalent present value. So P given A is a discount factor. We want to multiply this annual amount by, and then over 12 years, of course. And then 150 happens at the end of 6 years. That's a single payment in the future with respect to present. So multiplying it by P given F to discount it back 6 years, so over 6. And then this 100 occurs at 12 at the end of 12 years. Again, it's a single future payment. We want to find its equivalent present value. So P given F a discount factors that we use, and 12 because we discount 12 years back, so 12 years here rather than 6 years for the previous one. So now that we set it up, again, we can use interpolation and solve it to find the delta in IRR, or incremental rate of return, is 1.3%. So that gives us the incremental rate of return. Of course, we could use spreadsheets to simplify the computations, because as you can see, the rate of return analysis sometimes gets very involved. So what are the functions that are really helpful? Well, first is IRR function is helpful, but also the rate function, right? The rate function is used for the ranges. Sorry, the rate function is used for the opposite. For the rate function is used for the single payments or series of payments, and IRR is used for the range. So in both cases, we could provide an initial guess at which the numerical method will initialize in Excel. For the rate function, we have the n, the number of periods, and we can have the a and the minus p as the default options, but we can skip one of those and instead include the future amount f. And as I said, right, we could have the type difference in terms of the type here, and the type is usually set up to default as an AND of the time periods, and 0, type 0 is a default, which is the AND of the time period assumption. But if you wanted to switch it to the beginning, we could change the type to 1, and then it would use the beginning of the year assumption. So again, this is the internal rate of return, where we can not just have these specific structures that we discussed, but we could have the whole range of payments, and that would use the IRR Excel function would use all kind of structured payments that we can include into the range of values here. Alright, so that's what I wanted to talk about today. Thank you for your attention, and I look forward to talking to you next time.